Here is a combined summary of the two pages. This paper proposes a lidar-based localization and mapping (LOAM) system that exploits HD maps in autonomous driving scenarios. The system extracts information from the drivable area and ground surface height components of HD maps to construct 4 DOF pose priors, which are then integrated into the post-graph optimization problem to create a globally consistent 3D map. HD maps play a central role in autonomous driving systems, and their accuracy and global consistency are crucial for successful operation. However, current SLAM algorithms suffer from drift accumulation and lack of global consistency, particularly in GPS-denied environments. To address these issues, this work proposes the use of HD map components as prior information to optimize the SLAM trajectory and generate a globally consistent map aligned with global coordinates. The proposed method is built upon a traditional lidar-based SLAM algorithm and ensures accurate localization and mapping results for long-term applications while making the system robust to challenging environments. The primary contributions of this work include the construction of prior information for a SLAM algorithm from HD map components, the introduction of a post-graph optimization scheme with HD map-based factors, and the demonstration of significantly higher accuracy compared to current state-of-the-art LOAM algorithms. Existing lidar-based SLAM algorithms have limitations, such as the need for loop closure detection or GPS data, which can be unreliable in certain environments. In contrast, this work utilizes compact HD map components, which offer a compact representation with minimal memory usage, making them suitable for real-time SLAM. The proposed method is a first step towards enabling HD map change detection and updates, which is essential for long-term navigation in familiar environments. Here is a combined summary of pages 3 and 4 of the research paper. The authors propose a novel approach to leveraging high-definition, HD, maps for post-graph optimization in simultaneous localization and mapping, SLAM, systems. They utilize vector maps and raster maps from the Argovers 2 TBV dataset to create a comprehensive HD map representation, comprising lane graphs, pedestrian crossings, drivable areas, and ground surface height information. The authors introduce notations for physical quantities, estimates, and measurements, and define the vehicle's pose as a tuple of position and orientation. They also define the residual between two SE3 poses and the notation for the norm of a vector. The HD map components are described, including lane graphs, pedestrian crossings, drivable areas, and ground surface height maps. The authors then formulate the problem statement as optimizing a post-graph cost function with prior HD map constraints. The methodology involves a two-section system: SLAM algorithm and prior map constraint computation. The SLAM algorithm uses 3D lidar point clouds as input and builds upon the LOAM approach, incorporating keyframe registration and post-graph optimization threads. The prior map constraints are generated by matching keyframes to the HD map. The authors describe the process of generating prior map constraints, including preprocessing, scanto map matching, and altitude constraint estimation. In preprocessing, keyframe information is used to compute prior map constraints, and the pose is decomposed into yaw, pitch, roll angles, and translational components. Scantomap matching involves computing a 2D transformation by matching road points from the keyframe point cloud to the drivable area vector map using normal distributions transform (NDT) scan matching. The optimized 2D pose is used to construct the 3D pose prior, and the covariance of the observations is determined. Altitude constraint estimation involves using the ground surface height map to obtain a robust estimate of the current altitude. The final HD map pose prior is assembled by combining the optimized yaw, pitch, roll angles, and translational components. The author's approach enables the integration of HD map constraints into SLAM systems, enhancing accuracy and robustness in challenging environments. The authors present a lidar-based simultaneous localization and mapping (SLAM) algorithm that leverages high-definition HD map components, such as drivable area maps and ground surface height maps, as prior information for pose graph optimization. The algorithm builds upon the LOAM framework and incorporates a keyframe registration strategy to compute prior map constraints. These constraints are then used in an incremental smoothing and mapping ESOM2 algorithm to optimize the pose graph. The authors evaluate their approach using the Argovers 2 TBV dataset, which consists of 1043 sequences with an average duration of 54 seconds, acquired in 6 different cities. They compare their method with 3 state-of-the-art lidar-based SLAM algorithms, LOAM, FLOAM, and direct lidar odometry, DLO. The results show that their proposed approach outperforms the baseline methods, with a significant improvement in accuracy, particularly in challenging scenarios. The authors perform both quantitative and qualitative analyses to evaluate the performance of their approach. Quantitatively, they report the mean, median, RMSE, standard deviation, and maximum absolute trajectory error, 8, for each method. The results demonstrate that their approach achieves the lowest RMSE, with an improvement of up to 45 centimeters compared to LOAM. Qualitatively, the authors analyze the performance of each method on 10 selected sequences, showcasing the robustness of their approach in various scenarios. They observe that their method consistently produces accurate results, even in cases where the baseline methods fail. However, they also acknowledge some limitations of their approach, such as the reliance on the quality of the drivable area vector map, which can impact performance in certain scenarios. The authors conclude that their approach can generate highly accurate results in challenging scenarios, making it a promising solution for lidar-based SLAM applications. This paper presents a comprehensive literature review on various aspects of lidar-based perception and mapping for autonomous vehicles. The authors provide an extensive list of references, covering topics such as dataset creation, simultaneous localization and mapping, SLAM, lidar odometry, and mapping techniques. The paper begins by citing several datasets for robot perception, including the MCD dataset, Hilti-Oxford dataset, and Newer College dataset. These datasets provide diverse environments and scenarios for testing and evaluating autonomous vehicle systems. The authors then discuss various SLAM techniques, including LOAM, Lego LOAM, and Fast LOAM, which are designed for real-time lidar odometry and mapping. These methods utilize iterative closest point, ICP, and Kalman filter-based approaches to achieve accurate and efficient mapping. Lidar odometry techniques, such as LIOSAM, Fast LIO, and direct lidar odometry, are also reviewed. These methods focus on tightly coupled lidar inertial odometry, ensuring robust and accurate localization. The paper also explores mapping techniques, including graph-based SLAM and constrained SLAM. These approaches leverage publicly available maps, such as OpenStreetMap, to improve localization and mapping performance. Furthermore, the authors discuss various point cloud processing techniques, including segmentation, feature extraction, and registration. These methods are essential for effective lidar-based perception and mapping. The review highlights the importance of evaluating SLAM systems using standardized benchmarks, such as the KITTI dataset and the TUM-RGBD dataset. These benchmarks provide a common platform for comparing and evaluating the performance of different SLAM systems. Overall, this literature review provides a comprehensive overview of the state-of-the-art in lidar-based perception and mapping for autonomous vehicles, highlighting the key challenges, approaches, and evaluation methods in this field.